force diagrams have been pretty easy so far. This is where it can get a little more difficult. So here we're dealing with forces on an angle or an incline. So the first thing it says, surfaces push perpendicular to the object, meaning straight up. So we have been dealing with surfaces that have just been horizontal. So we have always said, well, Earth is going to pull down and that surface is going to push straight up, which you are absolutely correct. And we can show that it pushes straight up because we're going to form a 90-degree angle with that up force and with the surface, how the surface is angled. But if we change that surface and we now put it on an angle, that surface is still going to push directly straight up. If you want, you could actually turn your paper so now that line is horizontal, and you're going to still draw it in the exact same direction, straight up, and we're going to still get that 90-degree angle there. Or if we slant the surface in that direction, that surface is going to push directly straight up, where you get a 90-degree angle with that vector and the surface. So if we have a vector that's drawn on an angle, we're going to have to separate that force on an angle into the components back when we did our forces or our vector unit. When a force is in its components, we can actually ignore or neglect that original force, that force that's on an angle, when we're trying to determine the overall net force, to determine if we have a balanced or unbalanced force diagram, to determine if we are at rest, moving at a constant velocity, or we're accelerating. So the only time where we will draw our components a little different than how we did it back in our vector unit is when we draw our normal force. And again, here it says the normal force. That's just the surface's vector. So if we're talking about a book on the table, the table pushing up on the book is also known as the normal force. If I'm holding my pencil up in the palm of my hand pushing up on the pencil is also known as a normal force. So if on a ramp or an incline, you draw the normal force or the surface's components down in the direction of Earth's pull. Or another way you can word it is you'll take the force of gravity, the force of Earth's pull, and you'll break that up into two components. One that is perpendicular to the normal force or the surface's force, just in the opposite direction. And the second component is drawn parallel to the surface. And we also need to remember that when you draw in components, the components will always form a 90-degree angle. So I mentioned this word normal force on the last slide. So again, a normal force is a force exerted by a surface. The word normal means perpendicular in math, and normal forces are always in the direction that is perpendicular to the surfaces in contact. So on some worksheets, or if you looked on websites or in the book, you might see this term normal force. It's just the direction of how the surface is pushing on an object. And it's always going to push to form a 90-degree angle with that vector and that surface. You also might see this word tension force. So we haven't used this term tension before, but we've said string or rope or cable or wire. All those types of objects have tension in them. So if we have an example, a balloon is being suspended by a string, well, instead of labeling that the force of the string on the balloon, that's also known as the tension force. So you may see those two terms on some worksheets. So again, normal force is just talking about the surface, and tension force is just it's dealing either with a string, a rope, a cable, or a wire. So we've talked about this term terminal velocity before in class. That's when the downward force of gravity is equal to the upward force of air resistance. And in that case, when we draw a force diagram with something that has terminal velocity, we draw our object, our dot, and we draw a vector down. So that would be the force of Earth on the object. And we also now know from our mass and weight lab that if this is an object that has a greater mass, this vector is going to be much larger because Earth pulls more massive objects. And so if it's falling at a great enough velocity, the air resistance is going to keep increasing as the velocity increases until it reaches a point where the upward force of air on the object is equal to the force of Earth on the object. So now we have a balanced force diagram, and you'll be falling at a constant velocity. Well, yes, we can also have an example where the force of air is, this vector is longer than Earth's pull, which means it's kind of maybe like an example of you having a parachute where you're not going to, you're still going to, you fall down, but you might be, it's going to just take you a longer time due to the air resistance being a little greater. I will never ask you to calculate this in class, but some students have been interested in how to actually calculate the amount of air resistance. And this is the formula that scientists use to calculate the air resistance on an object that is falling. So if you're interested in this, you can kind of look it over and ask me questions if you have any, or just skip on over. So here we have two examples. They actually are on the back of worksheet 5.2, and these are dealing with objects that are two-dimensional. Some of them are on ramps and some of them are pulled at different angles. So on number 10, it says static friction prevents sliding. So we have this block on this inclined surface and it's not sliding down. Static friction, we have a whole nother set of notes just pertaining to friction, but static friction means at rest. So whenever you see this word static friction, just know velocity 0, it's at rest. So without friction, this block would slide down the ramp, but friction is holding it up the ramp, so it's not sliding down. So this is our example where it's one of the times where we will not draw the components the same that we did back in our vector unit. So I'm going to ask you to first maybe draw the forces on the picture first, and then we'll draw it over here on the right just to make sure everything looks correctly. And since it's static friction, it's at rest, we want to draw a force diagram that is balanced. So let's start off by just drawing it on the block. So I'm going to draw a vector, our dot right there. And then we always have our one non-contact force, which is Earth's pull, gravity. And gravity always pulls in the exact same direction, which is straight down. The force of Earth on the block. And then we, like I stated before, surfaces push perpendicular. So since we have our inclined surface that's slanting down, this surface is going to push perpendicular. It's going to be, you want to draw a vector up, that it forms a 90-degree angle with this surface. So right now it doesn't matter how long or how short that vector is. We'll eventually have to adjust the length. So that's going to be the force of the ramp on the block. So that vector is up and to the right slightly. Okay? And then we know static friction, so like I stated before, if there was no friction, this block would slide down the ramp. So friction, the block and the surface are in contact, friction would be in the opposite direction of the motion if it was moving. So the friction is going to be up the ramp. And again, the length of the vector doesn't matter right now. We'll eventually have to change that. So this is lowercase f, the frictional force of the ramp on the block. So in order for us to determine if this force diagram is balanced, we need to start drawing in some components. And so I'm going to word it one of two ways. You can either take the normal forces components, which is the ramp's components, and draw it down in the direction of Earth's pull. So you draw it, flip it down. Instead of drawing it to the right and up, we draw it down in the direction of Earth's pull. Or we say that we take this, the gravity, the force of Earth's force, we take this and break it up into two forces, one that's perpendicular to the normal force, just in the opposite direction, and one that's parallel to the surface. So both of them mean the exact same thing, it's just kind of slightly worded a little differently. So I always tell it the easiest thing to do is to take this up vector and flip it down. And so we want it to draw it in the exact same length, just in the opposite direction. And these are components, and components are always drawn as a dashed line. So we're hoping that this blue line is the exact same amount, exact same length as this up arrow that we drew for the ramp. The next one is we draw one that is parallel to the surface. So parallel would be like this. And again, the components are always going to form a 90-degree angle. So starting at the head of this one, I'm going to draw a vector that's parallel to the surface. And what ends up happening is that this becomes the resultant. And we always draw the resultant in from start to finish. So what we'll need to do is we'll need to adjust the length of this vector slightly. And it's not letting me erase. Let's see. No. So I'm just going to extend that vector down. So the head of this vector down meets up with the head of this component. Typically, we always also say that horizontal is X and vertical is Y. Okay, so this, yes, the Y has a slight horizontal and a vertical, but since we drew this with this is our normal, it's pushes perpendicular, we'll label this one Y and this one X. So drawing it over here onto the right side, we have our dot, our object. We have Earth pulling straight down. We have the ramp pushing up to the right. We have the friction pulling up to the left. And then we draw our components. X, Y, force of Earth on the block, force of ramp on the block, and this is the frictional force of the ramp on the block. So this is how we determine if it's balanced or not. So we have this vector here, our X vector. If you look, it's parallel, should be parallel to this friction, because friction is always drawn in the exact direction of the surface. So this up and to the left is the exact same length as this down and to the right, because again, we need a 90-degree angle here with my components. And like I said again, that the Earth right here becomes the resultant. And the Earth, the head of the Earth vector needs to match up with the head of that second vector, or the component, sorry. So this cancels out with this. And again, these are this Earth's pull vectors. So we can essentially ignore this vector, ignore this red line down, and just pay attention to these blue arrows. So if this cancels down and to the right, cancels this up and to the left, this down and to the left cancels this up and to the right. So here overall we have a balanced force diagram. So we'll do more examples of objects that are on ramps. That's the hardest one for students to wrap their mind around. The next example is going to be pretty simple, because it's going to be very similar to the ones we did back in our forces unit, or our vector unit, sorry. So we can start off by drawing it on the picture. And we always have our one non-contact force, which is going to be the force of Earth pulling down